did last time. And let me just share. Okay. What I would like to do, I will review some of what we did last time, because I know last session wasn't easy. And then we continue. We talked about the what happened here? Okay. We talked about the multivariables linear regressions, which kind of estimating the GDP of a country based on other 4 variables. Okay, and we dealt with the issue of how the computer really actually trying to find that relationship. And I talked about the simple case first, in which you use a descended. One sec. Yeah, here we go. And that's what we did last time, by the way. So that's what we did last time. This time we tried to estimate. In fact, we're using a multi-layers neural network to try to predict based on an image of a writing, a picture, okay, can a computer identify which number it is? So we're giving a lot of pictures like this to the computer, train the computer, and then based on that, we're giving him an examples, and then trying that the computer will identify which number is handwritten, okay? Now we said, the way the computer does it, well, it is trying to find all those parameters so the numbers, the results will match the input. What did I mean by that? But before I went into that, I said, let's take a simple example, even simpler than this one. So just to understand how the computer works. So let me go back to this one. And I said, let's say, okay, we're just taking a pause and now we'll come back to what I just trying to solve with multi-layer neural network. In the case that we have a sample, a very simple sample, we have a relationship between the y and the x, okay? Let's say I'm observing one variable, the x number is going from 1 to 20, and that's the measurement of another variable. And now I'm trying to fit the relationship between the two, okay? Now I'm assuming that the relationship is this kind, okay? Y equal to q squared minus x squared plus x. Okay, but I don't really know what the q is. And I'm trying to estimate what the q is such that I can see the relationship between the x and y. How can I do that? Okay. And the way we do it, and I said last time, okay, we said, okay, we can assume some q. Let's say I'm guessing the q is 1. I don't really know. The only things I know is that one. And I'm assuming that this is the relationship, but I don't know the q. So one way to go about it, and that's the way we usually do, and the computer does, we take some random number of q. I said, okay, if this is the q, okay, what will be the relationship now? And then we said, okay, we just put this equation here that shows the relationship between x and y based on this equation when q is 1. And then all the y's turn to be 1, yeah? And that's just simply because when q is 1, it's q squared, that means 1 minus x plus x. Okay, in that case, plus x minus x is always cancel out, and y is always 1. So no surprise we're getting this one. Then if I change that one, and then we want to focus, how do I change the q? But for now, if I did randomly and I move that, change that to 2, let's say intentionally I'll put 1.5. Okay, and now I do the whole calculation again. I'm getting a different y. Okay, this is the right q? How do I know that? So one way to do it, it's saying, let's take the difference between this one, okay, that if Q is 1.5, okay, those Y is supposed to be close to what I see in reality. These are the numbers that I measure in reality. So I said, okay, let's see the difference. So we take the difference for each one of them and we get this column. This column is basically the difference between this column and this column. We take the difference, and then in order to make sure that all the differences will be positive, we square it, okay? We square the difference and we add them up. So we're getting a number here. Let me even mark it. Let's mark it with a different color. I put a white yellow here, okay? And okay, so this number is the sum square of the difference between what we measure in reality and what should have been if the Q is really 1.5. But we really don't know the Q, and we're looking for that Q. Okay, we're looking for that Q. Now, if this number is very low, then we can say, well, this is probably the right Q. But we're trying to play with it. So if I change this Q, let's say to 0, let's say I think maybe the Q is 0. And what's going to happen to the difference? The difference will be high because I'm getting away from the true Q. If the Q is 3, if I think it's Q is 3, I get another measure. And you know, I really want to find or try to find the real Q. So what happens if I put the Q3 and I realize it's a high number? What happens if I change it to 2.5? Oh, the difference between this column and this column square becomes to be even lower. So it means I'm in the right direction. What happened is when it's worth 3, reduce the Q, it went down. So maybe I should reduce it, continue reducing it. How about if I reduce it to 2.25? Oh, it went down more. Well, I'm in the right direction. Okay? Fair enough. Now, ideally, okay, I said, okay, let's reduce it by another, let's make 1.75. Sorry. Let's do 1.75. Well, the number is still high. Maybe I moved too much to the right. How do I know if I move too much to the right? Well, if I increase it, I will decrease it to 1.5. Remember, I'm reducing the Q. If I go to 1.5, attention, the number went up. Okay, there was a number before that probably is the right one. So I maybe went too much down with the Q. Maybe I should go back now. So maybe I will go back. Instead of 1.75, I will do it even 1.9. Oh, wow, this is even lower. Okay? I'm getting closer, that number going down. If I go back to 2.2, right, the number is higher. I probably passed too much to the left, to the right. So maybe I will decrease it a little more. In fact, we know that the right number is 2. That's the way we built it. Okay? The question is, how can I find that number? You know, when you study in statistics or in mathematics, okay, you will take the derivative of the function, the derivative of that function, and you equal it to 0, and you get the answer. In fact, the derivative of yq squared minus xq plus x, if you take the derivative by q, that is the answer. It's 4 minus x. And that equal to, and that's equal to, sorry, is that right? How do we do that? Hold a second. We have, no, it depends on the x, sorry. If the x is View here. Yeah, here we go. And we will have ready to use specific x. If we use x equal to 4, and we'll put it here, this will be the equation. If you take the derivative of that, it will be 2q minus 4. And then the result will be q equal to 2. So that when q is equal to 2, you get the minimum point, okay? But the computer doesn't do it with a derivative. And there's a reason. Because sometimes you will have so many parameters. Here we're doing only with one parameters. But if you have many parameters, okay, doing derivative and equal to 0 would be huge matrix, and you won't be able to, it would take forever for the computer to convert it. I won't get into that one. The only things I said, the computer doesn't do it this way. The computer does it a little, looks like primitive, but it isn't, okay? It does take the derivative, okay? And then he changed the results. For example, when I'm in q equal, let's take q equal 3, and he takes the derivative of that, okay? So if I take this one, for example, and I take the derivative, let me write the derivative here. This will be 2q minus 4. Okay? In a point when it's 3, you will see 3 times 2, it's 6, minus 4 is positive. That means when we are here in the picture, when the q is 3, the slope is positive. When the slope is positive, that means when you increase the q, the value of the function will keep going up. No surprise. In fact, that's really what's happening. When we're putting a q, which higher, let's say I will put 4, you will see. When it's 3, you're getting this number. If I put a higher number, means a higher q, that square will go up. Here we go, let's try it. 4, no surprise, because the derivative is positive. What happens when the derivative is negative? What happens if we take q equal to 1? Okay, when q is 1, okay, the derivative is negative. 1 times 2, it's 2, minus 4 is minus 2. The derivative is negative, meaning we are in this point, okay, below the 2, which is the minimum. So if we are left to the minimum point, the derivative will be negative. Then we'll have to increase the q. If we are on the left one, the derivative is positive, we have to reduce the q. Thank God we don't have to do it ourselves. The computer will do it himself. The computer will take the derivative by itself. It will check if it's negative, okay? It will increase the q. If it's positive, it will decrease the q, and it will find the minimum. So all the games we're playing here in Excel, the computer will do it by itself. It will take the derivative of the function, okay? And it will find if the derivative is positive, it will take some random q like we did, okay? Like we chose like number 3, if you remember. It calculated the derivative, like here it's positive 2. It knows that the value we're getting here, to reduce it, we have to go to the left. It will reduce the q. If we put a number, let's say number 1 as we did before, you will see the derivative is negative. 2 times 1 minus 4, it's minus 2, it's negative, means it will have to increase it. And that's what the computer does. This one, I hope, it's a little hard, I know, for the first time, and a lot of people just get totally. The computer does derivative, it finds the value of the derivative for that q. If it's positive, it will reduce that q. If it is a negative, it will increase the q. And that way, it finds until you find the derivative. By the way, if you have more than one q, this example is a very simple one. But let's go back to our actual scenario. Don't forget, we had 784 parameters here, because we took a picture, as I showed the first, I think, last time or one before. We said that the picture, And what happened? Why it doesn't like me? Let me see. Yeah, we said that an image, here we have a number of 5. It's nothing but, why it doesn't like me? Anyway, it's hard to, let me increase it here. Okay, you can tell that an image is really a it's 2 dimension, okay, columns and rows, and the numbers is nothing but putting here the pixels. Every pixel, every small part, it's a number. If it's 250, if it's 255, it will be totally white. So all the white that we see in an image, they are close to 255. If it's totally black, it will be 0. So everything we see here, 0, it turns into a black number, a black spot, a pixel. But if it's 255, it will be totally white. And any number between, it will be a gray. And the higher the number, it will be closer to black. And if it's closer to 1, sorry, if it's closer to 0, it will be black. If it's closer to 255, it will be white. And any number between will be a gray number. This is the way we present an image. If we want to make it converted to one vector we talked about last time, we're taking each row and we're adding them up one next to each other. And then we're getting we'll get a vector of numbers between 1 to 784. 28 by 28, the size of the image we're taking in this example, 28 by 28, it's 784. So we have 784 numbers. Now, those numbers, okay, well, we take those numbers and multiply them by some Q, all of those each one of them will be multiplied, every number in this image will be multiplied by some constant Q. So you can imagine we have 784 Qs, much more complex than this example that we talked about here in the Excel, which is a very simple example. We have only one Q. This equation is only one Q. Here, on the other hand, we have an example that we have 784, and we try to minimize it. So we multiply those numbers by that Q and add them up, okay? And we try to get to this Y. You can think about that one in a minute. I will elaborate even more because this one much more complex than that, okay? But just to get the idea, we have so many parameters here, and we eventually try to match between those 784 numbers to really what that image is. So this one is really number 5. And then all what we would like to do, that this number 5 will match, it will match this number of the Y, okay? Theoretically, you can say, well, I want those 784 numbers to match number 5, but that's not the way we do it. In a minute, I will elaborate even further. But just can imagine, we're not going to do by hand like we did in the Excel, changing all those Qs. The computer does it for us. And the way it does it, it takes a derivative for each one of those Q, and it will move them up and down until it gets those 785 close to what the image is. And that's the way you find the right Qs. I hope that's clear. It's a little hard, I know. And I would just add one more element of complexity. It doesn't really go from the 784 directly to the 5. It goes by stages. What does it mean? This is another element which is hard. It goes from 784, in this example, to 512. That's why it's called multi-layer network. In fact, it uses a big matrix. I hope you know what a matrix is, but it takes 784 numbers, a vector, multiplied by a matrix that has 784 rows and 512 columns. Let me explain that a little bit. This is a little hard, but there's no really shortcut for that. Just imagine you have a matrix. I hope everybody knows what a matrix is. Why it doesn't like me? Is that, yeah. I'll just put some, this is really Q's. I really should write Q here. Q1, Q2, etc. And in fact, you really have 784 Q's like that. So this one really going to up to 784, okay? So you have many, many Q's, and there's a lot of those in the middle. I will just remove those so you don't get confused. But there's many Q's here, okay? And now the matrix is going, you have 784 rows, and you will have 512 columns. So this is really will be Q 512. And why did I choose those numbers? Okay, it really is the network that this one says from vector of 784, you want to convert it to a vector of 512. And how does it do it? It takes a vector of one vector, let's say I will call those one x1 to x2 to x3, etc., up to x784. It takes all those numbers. I just don't have enough space here on the Excel. I'm not going to put all of them. It will take this vector. It will multiply it by every. Why it doesn't give me that one to be a background? Yeah, here we go. Okay, and it will multiply it by this matrix. When you have a vector of 784 numbers, you multiply it by a matrix of this kind. It doesn't like me for some. Here we go. Let me see. Maybe we'll take this one. Yeah, here we go. If we have a matrix like this one, when you take a vector of 784 numbers, you take this number, you multiply it by this column, you will get a number. And you add them up, you get a number. You take the same one, you multiply it by the second column, you get another number here. So here you got the number, the first number, I'll just call it ZZZ, and then you get another one, and another one. Okay, so every time you take this vector, you multiply by a column, you'll get a number, etc., etc. You have 512. So that means you'll get a row of 512 numbers. Another word, in fact, it's like, let me just change that one to a yellow too again. Here we go. In fact, when you take a vector of 784 multiplied by a matrix of 784 by 512, you're converting this vector to a smaller vector that only 512. I hope you got it. If not, please go and look at your algebra. Okay, and if you need, I can make maybe a special, or maybe SEO or Opio can make a session on that. But I'm not really going to teach linear algebra here, okay? In other words, a vector can be shrinked or be smaller by multiplying it by a matrix that has smaller columns. And if I want to reduce a vector of 512 to a smaller one, to 256, we again multiply it by another matrix, that 512 by 256. So we keep doing it. Eventually, when we're moving from 128 to 10, okay, it will be a matrix of 128 by 10. In other words, the last matrix here, it will be a matrix, a small matrix that has only 10 columns, okay? We'll have like 10 columns. So let me make it like a matrix like that. I don't know how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So the last matrix will be of whatever number here we have 128. on 10. When you multiply this vector by this kind of matrix, you will end up with a vector of only 10 numbers. Okay, I hope that's clear. It really should be clear if you know linear algebra. Okay, and what the final result? The final result is this neural network, okay, take those pixels of many, many pictures, and then eventually I'm taking all those numbers, convert them to only 10 numbers. And there's another function we apply in the end, it's called softmax. It will take the highest number out of the 10. I can repeat it, it's a function called softmax. And this function takes those numbers, convert them to 10 numbers. And those numbers, okay, it takes the highest one and it will mark it. For example, if we get 10 numbers and the second one is the highest out of the 10, it will make the y to be number 2. If the highest number is 5, the highest number is in the 5th place, y will be 5. When it says and it gets the 5, then it will say, well, the image I have seen here, I classify it as number 5. If the highest number is number 9, it will say the image I have seen here, it is number 9. That's the way multi-layer neural network works. And that's the way really these images are. So stage number 1, it's really, really huge calculation. You cannot really do it with Excel. You will really need like a Python or one of those sophisticated program. So what do you do at stage number 1? In this example, I think we take about 60,000 images like this one, 60,000. And we run those 60,000, each one of them, okay, we take the image, we convert it to a long vector of 784. We go through this process and we get some numbers here, okay? Let's say I put the image of 5 and I saw it's number 4. That's wrong. When it's wrong, it means I need to change those parameters. So the computer automatically changed those hues, those parameters of the matrices, such that the number 5 will match number 5. An image of 9, okay, will match number 9. So it's keep changing those parameters of the neural network until all those 60,000 or most of them, okay, usually it would be nice if you have all of them, but even if you get close to 95, 98%, then you say, well, I did very good. And then after you match all those 60,000 and all of them kind of matching, then you can say, well, the neural network is already trained, meaning I learned all the parameters in the neural network. The next stage, you ask yourself, let's test it on another image we never have seen. Those images we haven't seen, we call them a test variables, okay? We call those a test one. For example, if I take an image, after I train it, I take an image, okay? I just clicked on it. Okay, it's number 7. Oh, hey, it's wrong. It took the image of 7, it put it here, it tried to look at it. Oh, 7 didn't come out right. So that means the training is not good. Let's try another one. 8, no, it's number 1. It means this neural network is not really trained. So let's train it, okay? Let's train it. We'll click on the train one. Let me just refresh the screen. Okay, we'll do the training. So I will start with one episode. We'll do more than one episode. We will need much more than one episode. Okay, it's running. Okay, and he told me the test loss is 0.11. Let's run it one more time. So you get what I really did. He only took 60,000 images, tried to match them. That's one round of epochs. That's called an epoch. When he took all the 60,000 images, tried to match them, and it got to some level. The accuracy was 96% already. But I'm going to run it to second time. Take all the 60,000 again and tell him, try to refine your parameters of the neural network. So I'm running, click again on the train. Let's do it one more time. Let's see what happened. Okay, you can tell that the accuracy went up, okay? It went to 97%, okay? And this is 2 apex. And you can tell that the loss function went down. It's really hard. I will run it maybe on, and let's do 10 more apex, and let's see what happened. Or maybe I need much more. Let's run it again. It's run on 10 apex. In fact, it's doing 10 times the 60,000 of images. In a minute, I will go over the code so you can get and see it. But let's wait a second. Let's see how that goes. I really hope at least you understand what it does is it takes so many images, like in this example, it's 60,000, and is matching the parameters of all those matrices. Just imagine how much work it does. And here we go, it's really nice. We can tell that the loss function went down. What does it mean, the loss? We call it loss. We mean like the square root of, in our example here, like similar to this one. This is really, the more is training it, is getting closer to the 2 in this example. And here it does, it's the same here. And that square, that difference, square is going down as I train it more and more. This is quite good. Let's say we get an image now. Let's say if we get, oh, beautiful, look at that. Remember, it got it wrong last time. Now it matched those parameters. And after it matched the parameters, number 7, you can really identify it as a number 7, which is really cool. And that's really the way it works, okay? Let's try another image. Let's take another image. Okay, took number 8. You see, got an image. It really very, it does so much work, by the way. When I click here, I'm sending a message to the server, and I tell him, take a random image out of the 10,000. I keep 10,000 aside, 60,000, I train the algorithm. 10,000, it's something that the algorithm haven't seen. I tell him, pick up random one. A random one, it took 8. He takes that image and he puts it through the network. The network calculate, and then he gets 10 numbers here in the end. And he looks which one is the highest number. He found that the highest number is the 8th one. And then he said, oh, why it's 8? And that's the way it works, okay? And that's beautiful. I run it only 10 times, which is not really a lot. And he's already is correct in 98% of the time. Let me click it one more time and see. Number 1, he identifies as number 1. This is beautiful, number 5. And it could be really different. Let's say if we can get another 5, 6, he identifies 6. This is beautiful. It can take an image now and it actually can predict which number it's referred to, okay? This is from the theoretical one, and I hope really you got the most out of it. The last one, which I really think everyone, you cannot really call yourself understanding AI unless you really know how to program it. So how we program it? Okay, let me go step by step, okay? And there is 2 layers of programming. One is on the client side. It really is this image, this screen itself. And the second one is in Python. How does it work in Python? So I go step by step. I will start with the Python and the JavaScript. I went over that a little bit in the other sessions, but I'll go over this one this time. Okay. What really we do when we click on the button train? Okay, let me do that this way. Control click. I will do cancel because I want to run it. And what is the code of this button? You can tell that the button does is basically using a function of this object. There's an object called MLNNDP. In a minute, I will say, how do we store it here? In another word, there is an object in JavaScript that has a function called train. So I'm calling that train one and sending him some variables here. And which variables am I sending it to it? I'm sending to it, one is, this object, so I can get when I get a response from Python, it will be able to present it. We call it the status object. It's this one. This is one variable we send it to this train function. The second one, how many epochs, meaning how many times to train it. Take all those 60,000 images, how many times to run them and train the algorithm. I wrote here number 10. You see this one? This is another thing that I'm transferring. This is this. Second is that I want to train the object from the beginning, like I never trained it before. That's just for convenient. You can ignore that. And finally, I'm giving him this image of the chart. So this is the last one. And then when he gets the result, I want him to print the result of the loss function. And that's what he's going to do. In other words, I'm calling a function train of this object, transferring to him several parameters, the status object, the number of epochs, where to give me the result, where to pen the result. I'm transferring it to that function. This function now has two things to do. It's sending this request to the Python on the server. The server will do the work and give me the result. And when I get the result, that function will have to go and pen that one here and give me the response in that object. Now, as a side, in fact, not a side, it's really as a major one, we managing communication between JavaScript to the Python by an object. And we have a way to write objects. This is the place we write objects. The objects we're using for that purposes is called NN data processing. That object, as you can tell, has a function called train. This train, in fact, get those objects that we just transferred in that part, and it calls in the bottom here, okay, is calling the train function, is calling the Python and transferring all those parameters. I won't get too much into that one. That will take another totally different course even, okay? But the bottom line is we're sending all those parameters to the Python. We're getting a response, and the response in a callback function. This one is a callback function. When Python is done, it's going to call this function. This function gets the result from Python in a data, and this data populating the response in this screen. I won't even need to go over all of that. It will take a totally complete session and more than a session really. But at least you get an idea that we have a complete package, how to communicate to the server. And then when we get a response from the server, we present the result right in here. And this is a response. Similarly, I will go over the next button, that the mechanism of communicating to the server and getting a response and presenting it, it's very similar. Look at this button. I will click on this one, okay? And it really works very, very fast. You see, he sent it already as I clicked. But here I can see also the code. The code is very, very similar. It's the same object, but it has a function called getImage. That getImage is a function of the same object we saw a second ago. This object has a function. What is it? What's the name of that one? Yeah, I thought this is it, isn't it? I think it's this one. No? Okay. Yeah, it's called getImage. So how come? No, this ML and sorry. I find it ML and here we go. This one has a function called getImage, and the mechanism is very similar. We get those parameters, okay? We send it to the object, to the server gets the results, and we send it to us in a callback function. We get a callback function, we populate in this case, is the status one, and we say which image it is. It's beautiful, it really is. So it's so clean in a way we communicate between JavaScript to the Python. Now it's the hardest one, and really the most interesting one and the important one. It's how we manage the Python side, okay, of this project. So let's go into the Python side, and here we go, we have that. Here we go. Let's see how it's organized. Let me just collapse everything here. And you can tell here that we always organize Python in a very simple way. We have usually those two objects. Those objects, this is really like specific things if you need some specific. In this case, we don't really need. This is relatively simple. As complex it is, it's relatively simple. Okay, so we don't really use much, but we always keep this kind of a structure. So, and another object called MLNN data processing, which is inheriting from this one, but it's also inheriting from another two objects that we use a lot. In this case, I don't think we're using it. We don't really use them. But in many cases, we have a lot of additional function to operate the Python side. So let's see which function we actually used here. We use the train to train the object, and we have the get image. So let's look at the first one. What does it tell to train the algorithm? Okay, so we're getting all the parameters here. Okay, we're getting the dict, which is all the parameters. Let me run it again so you can see the whole process, and I might even open it. Let me run. Let me put one here. So it will run again so you can see how it runs, but it will be a small one. Okay, it's running, you can tell. Is it? No. Yeah, it is running. What happened? I'm running it on the server. My apology. Yeah, my mistake. I'm running it on the server and I'm showing you on my computer. So what I will do, I will open my computer with similar function. Okay. And yeah, I will run the same things on my computer, which is really similar to the one you saw there. I'll run it here. And then you can see how the code works. So if I go down here we go. It's processing the whole algorithm, and it means I'll go step by step. What does it do? Okay, so we're getting basically, you can tell here, we're getting to this line, which is means from JavaScript, call the function on Python. This is a Python one, and it's just really for myself, I can see all the parameters we're getting, and we really do have one apex. Okay, there's the only thing that I'm sending it. Run and train the algorithm with one apex. What does it do? Let me go over that. The whole thing is done in this function. When this function is being called, it tells him do the training with one epoch. What does it mean? Or what does it actually do? First is downloading data from the internet. This function, you know, TensorFlow is one of the very interesting library, okay? And TensorFlow has many databases for training and teaching. One of them called Minst. This one is a beautiful database of handwritten pictures. So what we do here, we call it online. We download the data from the internet of 70,000, if I remember what it means, we'll find out, okay? It's downloading all those data from the Minst database from the internet. And he's organizing them by two databases. Those are two data frames, in fact, those two. You can tell you have the one you have for the training, and each image, it tells me what it really is means. So when you get a picture of number 5, this is the pictures, and this is telling me for every picture, it tells me which number it is. So if I have a picture of number 6, okay, so that will be the image, and that will be the telling me the number. The same things, I have extra images for testing. So when I click on on the image here, it really is taking it from the testing. When I do the training, it takes the images only for the training. So that's really basically the beauty here. Whoever organized the database, he's already organized those data in that way, okay? One thing we do, this is called normalization. If you remember, I talked about it a little bit. I mentioned it in the past. The images are between numbers inside the image. One more time. Inside the images, we said that those images are a lot of numbers from 0 to 55. For the algorithm to work best is to convert all the numbers to numbers between 0 to 1. How do you do that? Since you know that all the numbers are here between 0 to 255, if you divide all the numbers by 255, all the numbers will be converted to numbers between 0 to 1, okay? And that's really the objective of doing that. We're taking all the numbers of the images, dividing them by 255, converting all the numbers to be between 0 to 1. Why do we do that? Well, maybe some other time I will get into that, just because of the, eventually we're getting numbers, okay, that we want to compare them. Converting them between 0 to 1 makes the derivative that we talked about before. I won't get into that too much really for one session or for beginners. But this is a good practice to convert data to be between 0 to 1. So that's stage of normalization that we have done here. Okay? Next, okay? We make those ones to the numbers. Remember that I said those are the labels. If it's number 5, it's number 5. It's number 6. If the image is number 6, here are the labels. So this is images, and this is like a list of images. For every image, we have a list of what each image is. So if this one, let's say it's number 5, for the computer to work in the right way, we cannot just give him number 5 like here. The images of we convert them to a category. Let me spend a little bit on what this line actually does, okay? If you remember, I said when we're training the algorithm, it gets 10 numbers, okay? It gets 10 numbers here, and then it takes the highest number, okay? And that higher number, it said, this is my result. If the highest number, it gets a lot of 10 numbers here, 10 different numbers. How do I pick what is this image is? If the highest number is number 8, then I would say the 8th number, then I say the result is really number 8. So in order to compare these final results to the actual number 5, we take number 5 and develop, we make a little, this is a little hard and I will go maybe a little slower. This is called like hard coding, the professional name. Let's say I take every number, okay, from 1 to 10 and convert them to what is known as hard coding. What does it mean? I take every number, I make 10 columns now. And this one will be, let's put also number 0 here. And here we'll put 0, 1, 2, 3, 4. I think this is about, if I need, I will add more. Number 1 here, and all the rest will be 0. This is conversion of a number. Let me just make, I will copy all of those 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Okay. If you see, if the real number is 0, I'm converting it to a vector with 10 columns. And I'll put everywhere 0 beside the one that is the number. So if this is 0, I'll put a number 1 under this column. I'll put 0 everywhere beside the place of number 5. I'll put number 1 here. This is called hard coding numbers, okay? How do I convert number 8? Anybody wants to help? What do you say, Opio? Ezio, what do you think? Let me help you out. I will put 0 everywhere beside the column. Which column? Anybody? What should I do here? I should put number 1 here. That's really converting number 7 to a hard coding. Is that right? Okay. And the rest you can really imagine how you do it. Okay. Number 9. Everywhere will be 0 beside the last one. That will be converting. Now pay attention. Why are we doing it? If the real number is number 9, for example, and I want to compare the image to number 9, remember we have here the end of the network, it's not 10 numbers. And we're getting numbers inside here. We're looking for which one is the highest number. If it's number 8, for example, so we turn everywhere to be 0 and only number 8 to be 1. And if we want to compare it to really the one that we know, let's say if it's number 8, okay, we know that this one will be number 8. Instead of writing number 8 here, we already prepare the 8 to be hard-coded. So we'll have 0, 0, 0, 1 in the 8, and 0 in the last one. So when we're comparing this one to the actual one, it would be 1 next to the other. Therefore, if the network is ending with 10 numbers, that Y has to be with 10 numbers, and that we can compare them, okay? That's why we're converting all the numbers to a hard coding. We can compare not number to a vector, we'll compare now a vector to a vector. And that's why when we train the algorithm, we must take the numbers, whatever is the train labels, there's really a list of a lot of numbers. So every number, we convert it to a list of 10 numbers. All of them will be 0 beside one place, okay? That's really what we do here in categorical. To categorical, it's a function in TensorFlow that automatically does it. Takes a number, convert it to a vector, and put the one in the place that that number referred to, okay? We do the same for the labels of the test, okay? Then next, all right, this is just a parameter that I'm using intentionally here. And then finally, okay. Then we get into the last one. We have the model, okay? I kind of skipped by, I will go back to that. Why is this model defined, okay? When we create this object, me go maybe back to when we, what did I define the model? I think it's in here probably. Okay, let's see here. We probably define the model somewhere here. I don't really remember, but I will find it in a second. Here we go. Let's see. Here we go here. Oh, we have to load. I think probably here in this one. Here we go. Okay. Yeah, I know that it should be here. So in the init, that's when the object's being created, it will probably call this load function. Probably will call this load function. Let's see who is calling this load function. Control F. Find it. Here we go. Now this is in the image, in the training. Beautiful. Yeah, I kind of skipped it. I kind of jumped without noticing. This load function, okay, basically what it does is calling this one's internal function just for convenience, okay, is loading. I won't get into the when you're saving that image or whatever, but I was just going to actually is calling another function called create model. And what is this create model is? It's this one. Okay, in fact, I made it to have two versions. In the future, we might take a look at the other one. But let me just look at this one. Basically, what is the structure? You can look at this one. This is the really important one. How is the objects being created? How is the model is being created? Pay attention. He's getting an image of 28 by 28. By the way, this is part of TensorFlow library. Okay, this is the way this library, and there's other in the future, we'll see other PyTorch, Torch libraries that is extremely powerful also. But TensorFlow is very popular and it's written by Google. And this is telling me the structure of the model. What is the structure of the model? It takes an image of 28 by 28, and then is converting it to one column. This line to this line means it takes the image, like I mentioned here, it takes the image and converts it to a long vector. That's what the model does right in here. It takes an image of 28 by 28, converting it to a long column. And then from a long column is reducing it to 64, to 10, up to the point that, as I said, is reducing it to 10. In fact, the truth of the matter, this model is slightly different than the picture we have here. Because this picture says 512, 128, 64 to 10. If I wanted to have exactly this model, here we go. I will just show you how will I modify it, okay? I will basically will modify it that this one will be 512, 512, okay? And then if this is 256, I will just move it to 56. And if I want to add one more layer, 256, if I want to move it to lower one, to 128, one more, I'll just add another column, another row, 126, 128. And then for 128, I think we moved it to 10. Okay, now the model that I specified here match exactly the image here. Okay, so we made a little simpler, and we saw that the simpler one give a good prediction. The shorter method, so probably this is overkilling. Okay, and how many layers should you put in? It's a different topic. And that's a complex, and sometimes you try it several times until you find the best one. But the different topics, I won't get into that today. Okay, this is really just if you want to change the model to something else. But let me put it back. I just wanted to demonstrate for you. But really, there's no need to make it more complex than it is, because it is a simple one. Okay, and that's doing an excellent job. Taking an image, reducing it to 10. This is the model. So when we already created the model, when we created the object, and the model is ready. This load function does it. Now we're training the model. The model has a function called fit. The fit is the one that actually tells the computer, take the images and change the matrices inside, so that model can predict. And that's really what we're doing here. And pay attention, I'm giving him all the images and I'm giving him the labels. But remember, these labels already converted to a hotspot numbers. Okay, those vector, it becomes to be not just a number, it's a vector of 10 numbers, which will have a 1 to indicate which number it is. The computer takes that, train the model, and after it trained the model, it tells me the loss. Every epoch it does, remember, I'm giving him how many epochs to do. So when he's training it, I gave him the beginning, I gave him 1, and then I gave him 10. So if it's 10, it will do the whole feeding 10 times, and every time it will remember how much the difference between the real numbers to whatever it's estimating, that loss, what we call loss, it will keep those numbers for me. And in fact, I'm really keeping those loss, and then I'm actually in the end here, I won't get into the whole things. When I'm getting those numbers back, I get the loss list, so I can show it to you in here. So after the model is being fed, okay, after the fit equation function, which we have here, okay, it will keep the loss for every epoch, which I eventually, here we go, we're getting it here. I will send it back and I will show it to you. One more things we do, okay, which is there's another function called evaluate, okay? And this one gives me also the accuracy of the model. How accurate is the model? And that's really when you get the results here, how accurate it is. Okay, if you realize here, it says accuracy 98%. It's basically going to take all the 60,000 after you train the model and try to predict them. And it was right in 98% of the time. So this evaluate, it's another function in the model. Pay attention, what the beauty in the whole things. I didn't have to write the algorithm myself. It's algorithm that has been written and put in TensorFlow. All what I had to do is to know how to use it. So here I train the model, and here I evaluate it, and I know how accurate is the model. Fair enough? And that's the beauty in the whole thing. Moreover, I can do it on the trained one, or I can do it on the test images. Here I did it on the test, which is much more robust. You know, one way I can do the training on the image itself, the training images, which I use for the training, that will give me an indication how good it trained the model. But the best, how good it is using it really on the images we haven't used, okay? And that's the best way to do it. And the accuracy, 98%, it's very, very good, okay? Okay, good. So that's really concluding the code structure. I didn't go to all the detail. It's really almost impossible. And I just hope that you know Python enough to be able to follow it yourself. But, okay, and that's really the code for the training. One more last, and with that we'll conclude. We have another function when you click get image, okay? It's taking a random number, predict the number and see the result. That function in the Python, literally this one, which is very simple. This one just, okay? What it really does, again, loading all the images again. Okay, since you already have trained the model, I'm not going to train it again. The only thing is I'm taking a random number, a random image of the test images. This is like one randomly that I take out of the 10,000. Okay, I take that image and keep it. In fact, I'm keeping this image so I can really show it to you here. Okay, so you can see it here. And then I do, and actually here we go. We have the, you know, the feed. You really don't have to do the feed. It's just that I'm doing one extra one for some reason. I don't know why, but you really don't have to train it again because it's already been trained. The important thing is this function. I do a predict function, meaning I take the new image that I took randomly and I do a predict with the model. And this one tells me which number it thinks, okay? Pay attention, what I'm getting in the predict, it is not a number, it is a hard code vector. It's really a 10 numbers with a lot of zeros, which one of them has 1. And there is another function called argmax. The argmax takes all those 10 numbers and find the highest one. And the one with the highest one, it tells me what is the index of it. The index really is the number. And that's why I call it the predicted number. And I'm sending it back to you. When I get the number here in the prediction, okay, I get one and I just present it right here, okay? In fact, you can really look at it here. You get those numbers here. Maybe you can see, let me see if I can show it to you here. In the JavaScript, you get it back from Python. You get from Python, what is the prediction? We get the data, the status. Yeah, here we go. I get the prediction, here we go. The prediction really is the data that we're sending back here. The results sending me the predictions, which is really this number. So I'm getting this number from Python. It gets up to JavaScript. We're getting it in JavaScript and presenting it on the screen. We're presenting it right here. Okay. Okay, guys, thank you. That was a little long and hard, as I told you. Whoever wants to be really an AI person, it's required knowledge in JavaScript, required knowledge in Python, and you can really, otherwise you really shouldn't get a little bit linear algebra, not too much. Most of the stuff we had done, linear algebra you need to know to the extent of multiplying by matrices. It's all over AI, okay? There are more complex, much more complex mathematical things. I will just present it, but you really don't have to go through all of that. I will just show, this is like one book, very good book on mathematics of AI. This is a little complex. You don't really need to know that. I won't require to do that, to know that. It's a little hard. But knowing how to multiply vector by matrix, it's a must. And start getting knowledge of TensorFlow or PyTorch library, it's a must. Otherwise, you will get totally lost. Okay, guys. Thank you. Questions before we conclude? Can you guys hear me? Opio, SEO?
Yes, doctor.
I think
Can hear you.
you can stop the video. Yeah.